Hello, everyone. It is my great pleasure and honor to be here to present you the Science with the TianQin Observatory talk. My name is Yi-Ming Hu. I'm coming from the TianQin Research Center for Gravitational Physics of Sanya University. My talk will be composed of the four parts. That is, first, I'll give you an overview on the TianQin project. Then I'll talk about what kind of science can TianQin perform. Then I will talk about briefly the progress of TianQin, and last, to sum it up, as we all know, very familiar with the idea of the gravitational wave spectrum, that is, from low frequency to high frequency, each different frequency range corresponding to different detection methodology. And if we want to perform the millihertz gravitational wave detection, we have to rely on the space-borne gravitational wave detections. And TianQin is exactly this kind of detector aiming to detect a vast number of different sources within this frequency range. The TianQin is a geocentric configuration that is orbiting around the Earth and together with the Earth orbiting around the Sun. The arm length is square root of 3 times 10 to the 5th kilometers, using the laser interferometry to perform gravitational wave detection. So with this setup, we can have some basic idea of what TianQin would look like within the solar system. And you might ask why it gets the name of TianQin. It's basically because that in Chinese, Tian corresponds to heaven and Qin means hub. So basically, TianQin is a hub in the heaven that awaits the cosmic plug of gravitational wave, just like this. So because we set for these key components or the key parameters for the detector or mission, namely the acceleration noise, the positional noise, and the arm length, we can use this information to figure out the sensitivity curve for TianQin with this equation. And as long as we have this sensitivity curve, we can overplot that sensitivity curve with a vast variety of different sources and look at how well can we measure these individual sources. That is, how many sources can we observe and how well can we measure the corresponding physical parameters. With this in mind, we explore the possibility of TianQin on the detection of a variety of different sources, including the galactic compact binaries, the coalescence of massive black hole binaries, the extreme mass ratio inspirals, the inspiral of stellar mass black holes binaries, and the stochastic background, which is basically an addition of all different sources together forming this stochastic background. Apart from the actual observation of these different sources, we can also use these sources as a tool to explore our understanding of the universe. For example, we can use the detections of the different sources to trace the cosmic expansion, to look at how fast the universe expands. And we can also use this information, the detections of different sources, to perform some testings on some basic fundamental physics, like the underlying physics of the gravity, or to test the curl nature of the black hole, etc. But let's jump into the details. For the galactic binaries, we know from the observation and theory derivation, we know that within our galaxy, there are a vast majority of binary red dwarfs, but they are just so dim that within our current observation of electromagnetic observation, there's only like 100 or the order of that number available to us. So we look at these numbers and we ask, how many of them can be detected by TianQin? The answer is plotted here so that within these known sources, we can probably observe like a dozen of them within a 5-year operation time for TianQin. But we know that for sure, apart from the EM observed sources, we also expect to see a large number of unknown sources to us that is dark in EM but bright in gravitational wave, so that we also look at the detection prospect on these derived sources. And the number is here. So with 5 years observational time, the TianQin can make the detection of about 9,000 sources. And with TianQin 1+2 configuration, we can expect to see about 11,000 sources within 5 years' time. Now notice that for LISA, this kind of vast majority of binary white dwarfs will form this humming foreground that will limit the detection ability in certain frequency range like this. However, TianQin does not suffer from this foreground. That is because TianQin have a shorter wavelength, a shorter arm length, and that corresponding to a slightly shift towards the high frequency in terms of the detection ability. And this foreground, due to this vast number of white dwarf binaries in the low frequency range, does not affect TianQin significantly, as shown in this plot. So that with 5-year observation or accumulation of data, the foreground is almost comparable with the background noise. The paper can be found in this link. You can scan the QR code. In addition to the detections, we also look at how well can we measure the corresponding parameters. Say, for example, we can localize the sources with like 1 square degrees. And also, we can measure the physical parameters very well. For example, for the intrinsic parameters like the frequency, we can determine it very accurately to an accuracy of 10 to the minus 8. Apart from the galactic binaries, let's look at the farthest places we can see the very massive binary black holes. From the observation of our Milky Way, the motion of the stars around the very center of the galaxy, we know there is a massive black hole in our galaxy. And we know also that from the observation of the N87, there is also a huge massive black hole within the center of that galaxy. So massive black holes do exist ubiquitously. And we also know that the galaxies will merge. Followed by these galaxy mergers, we expect to see the merger of the massive black hole binaries. And these mergers of binary black holes can emit very strong gravitational wave, and which can be determined and measured through the observation of TianQin. So just look at this plot. Within this range of mass, when it's appropriate, any merger within the observable universe can be easily detected by TianQin. So this is showing the horizon reach of TianQin. As long as it's within this mass range, any event happening in this mass range can be detected. But the problem is that we do not know these models of the massive black hole binary evolution very well. The way we treat the problem is just to use all possible sources, all possible models to have a comprehensive understanding of this massive black hole binary merger history. We use these 5 different models for our calculation. The bottom line is that if we assume the seed model for massive black hole is coming from this so-called heavy seed model, that is the direct collapse of a massive cloud of mass into something like 10 or even 100,000 solar mass into a black hole, then TianQin can basically see every single merger within this universe. Well, if it's coming from the light seed model, which a lot of these seed black holes are actually only about 100 solar mass, then many of these mergers cannot be detected by TianQin, but we can still see some part of these mergers. And just by looking at the distribution of the masses, we can try to distinguish different seeding models. We look at the 2 example cases. For example, if there is a merger happening in the very early universe, just after the birth of the black holes. By looking at them, we have high enough SNR, and we can have high enough parameter measurement ability to distinguish the mass value as well as the distance, etc., so that we can pinpoint the formation mechanism for this massive black holes. We also look at this possible scenario that one such merger happened very close within the redshift of 2. Then we ask ourselves, can we use this information, the data accumulated all the way before 24 hours before the merger? Then use this information to derive the information of the black hole binaries. The answer is yes. We can use this information to issue some alert of the final merger and pinpoint the location to an accuracy of several dozens of square degrees, and tell the telescopes where to look, when to look, etc. I'm running out of time, so I will be very brief. Apart from these binary white dwarfs and binary massive black holes, we also have this combination of a very massive black hole and a very light black hole, which is so-called extreme mass ratio inspiral. And the model for these systems are even less secure, so that in order to understand all possible scenarios, we look at all the possible combinations of the properties, including the massive black hole mass distribution, the spin distribution for the massive black holes, the m sigma or the mass velocity spread relationship for the galaxy, etc., to help us to build this very complicated and comprehensive catalog of different models. The bottom line is that with a lot of different physical setup, the merger rate is quite different. We use the tool again with the known gravitational wave caused by this AK waveform, and then cut it off at a certain frequency range according to 2 different conditions. One is assuming the orbit ends in Schwarzschild system, the other assuming a curl system. Then we look at this waveform and then put into the mechanism to calculate the SNR, the parameter space, parameter accuracy, etc. The result is that with TianQin, we can almost see every single, we can almost certainly observe some memory systems, except for the most pessimistic model, the M11. And overall, the event rate is very low. Except for this model, we can observe and some certain memories with TianQin. We also expect to measure the parameters very accurately for the intrinsic parameters to an accuracy of 10 to the minus 6, and to extrinsic ones, still not bad accuracy. We can also use TianQin to observe the stellar mass black hole binaries. Now notice that because the TianQin has a shorter arm length, it has a better sensitivity compared with LISA in high frequency, and has a better prospect of detecting such stellar mass black hole inspirals because they have higher frequency information. We use the information for the properties derived by LIGO-Virgo observation, and then calculated the detection rate, which is quite high, comparable with LISA or even better. And we also expect to see some certain parameters very accurately, like the chirp mass, the spin, etc., the eccentricity, etc. We can also determine the stochastic gravitational wave background with TianQin, and we can use the TianQin observation of the rain-down signal to put some constraint on the possible deviation of the no-hair theory, or even put some certain alternative theory of gravity into examination. Here in TianQin, we also started the looking of the data analysis with TianQin data on certain sources. I'm running out of time, so I won't go to the details for the TianQin progress, but please scan this QR code and go to Professor Ye's talk on the detailed progress. To sum it up, the TianQin project has made significant progress on the lunar laser ranging and on the TianQin-1 satellite. So very encouraging results aheading. And for my talk, to sum it up, Tianqin can expect to see a large variety of different sources and can measure the parameters very accurately. And please be aware that we constantly hire and offer job positions. So if you know anyone seeking for a job, please let us know and contact us. Thank you very much.